Greetings from Calgary. When working on Gadgeteer projects, sometimes you can't find a suitable existing Gadgeteer module. But don't worry, as breadboarding your own sensors and such with Gadgeteer is very simple. And if someone has breadboarded what you need, then it can be very easy to share. This project is an example of how easy it is to share breadboarded solutions with Gadgeteer. So simple, in fact, that people using this don't need to understand the details of the hardware or even the low-level code. To them, it appears to be just another Gadgeteer module. All you have to do is follow some easy instructions to wire it up, and it can be shared with more than just Gadgeteer projects. With small changes to the code, you can use these with a Raspberry Pi, running Windows IoT, for example, with a Fez Cream. Or given the source code is written in C#, you can use this code with .NET Microframework or .NET. So this is really a powerful way to share code across a broad and expanding user community. I needed some temperature probe devices for a project I'm working on, so I grabbed a couple of different ones from Adafruit to experiment with. I got an analog devices AD8495 and a Maxim integrated MAX31855. Both of these are K-type thermocouple devices, so they're inexpensive and will work for the project as we're measuring the temperature of a biomass reaction. A thermocouple is a device consisting of two different conductors welded together and produce a temperature-dependent voltage as a result of the thermoelectric effect, or more precisely, the Seebeck effect. Now this voltage is really small, in the order of 41 microvolts per degree C, so an amplifier is needed, hence the AD8495 and the MAX31855 chips, and why they're called thermocoupler amplifiers. I should give a bit of a shout out to material engineers, as IoT isn't just electronics and code, it's also material engineers coming up with cool materials for sensors and such. Note, I'll include links for everything below, including my driver source code on GitHub. Let's start with the driver for the AD8495, as it's a very simple analog device that, using with 3.3 volts, has a temperature range of -250 to 410 degrees Celsius. So basically how this works is that there's a power in connection, a ground, and then there's an output voltage that we connect to the analog pin. In Gadgeteer, this would be an A-socket device, and we measure this output voltage on this pin, and then once we have that, it's a very easy calculation to get the temperature. Input voltage minus 1.25 divided by 0.005, and that gives us the temperature in Celsius. The sensing accuracy range is about ±1 degree Celsius around room temperature, and about ±2 degrees Celsius for -25 Celsius to 400 Celsius. And given how simple this chip is, the power requirements are really a non-issue, as they are less than a milliwatt. So if we take a look at the code here, you'll see I've got some, this shows up in the documentation of how to wire it up. And remember, this is only to be used with 3.3 volts only. The analog pins on Gadgeteer handle up to a maximum of 3.3 volts. So if you connect this to a 5 volts, and you could damage your CPU. So looking at this, we create the socket, and we check to see that it's an A-type, it's an analog, like I said, and we create this analog input factory, and we're going to put it on pin 4, connected to pin 4 on the A socket. And then what we can do is we can read the voltage from the input pin, and then we take that minus 1.25 divided by the 0.005, and that gives us our temperature in Celsius. Now I've added a property to this module of a single point offset calculation for calibration. And then we can also have the temperature Fahrenheit. We just convert the temperature Celsius to Fahrenheit. And I've also included a read voltage, so you can get what the voltage was that was read and the proportional voltage between 0 and 1. And then, like I said, I've built this into a Gadgeteer module. And so if you're using Gadgeteer, all you have to do is install the module driver and it appears on your toolbar with all these routines. So that is, and I'll do a demo app here at the end. So that's basically all there is for the driver for the AD8485. Like I said, it's really simple to do analog devices with breadboarding. So switching over to the MAX31855. It's a little more complex than the AD8495 and uses a very simple SPI interface. And since it's read-only, we can fake this with general purpose I/O pins. It has a measurement range of -270 to 1372 degrees Celsius and a temperature resolution of about 0.25 degrees Celsius. Again, at very low power, just a tad more than the AD8495, but you get a little more from this chip than you did the AD8495, in that you get some air condition reporting and such. So how we wire this up: 3.3 volts into here. Of course, we have a ground wire. We have our data out. We put that on the pin 3, clock goes on the pin 4, and the chip select goes on the pin 5. And wire that up and you should be good to go. So looking at the code, we can come in here. Of course, again, I got my documentation here on how to wire it up. We have the chip is able to detect some different kind of faults. So we have a no fault detected indicator, a short to power, short to ground, an open circuit, general fault, and I have some out of range calculations as well. So basically, like I said, we're going to kind of fake an SPI interface. We have a clock, a chip select, and a master in, slave out pins that we need to do. We default, of course, to the fault conditions being okay. And with this chip, there's two temperatures. There's an internal temperature and a thermocouple temperature that we're going to have. So again, we're going to connect up to our socket. We check to make sure that it's an X or Y. We create an input on for pin 3, and that's going to be our data in. And then we have outputs to pin 4 and 5, which is the chip select and the clock. This is our offset. It's just a double that we can give it. It's a single point calibration correction. And then we come down here and let's have a look at how we do this read. So what we're going to do is we're going to get the data. So first thing that we have to do is we have to set the chip select pin to low. So we're going to take that, write that to false. I like to give it a little bit of a sleep just so the chip can be woken up. And then we're going to go through and we're going to kind of almost fake a clock cycle here, where we're going to set the clock right to high. We give it a little bit of a sleep so the chip can realize that the clock's gone high, and so that it puts the bit of information that it has onto the line, and then we can read that. And then we're just going to bit shift this over into data. And then we can set the clock to false. So then we're just going to repeat this process 32 times, and that gives us our data from the chip. And then we're going to put the clock select, we're going to put that, the chip select to high, and that indicates to the chip that we're done with it. Now again, with an SPI, that you were able to have multiple chips using the same SPI bus kind of thing, and so this is how you selected the chip, who was, what chip you're working with. So we're going to come in here. So the first 3 bits in our data are fault indicators. That so the chip's able to give us back some information whether or not there were some faults and such. And so if we get anything other than basically a no fault condition, we just set our temperatures for internal and to not numbers. And then we peel off those 3 bits and another bit, which is just a reserve bit. And so now that gets us into the internal temperature. And the internal temperature is 11 bits of information. And so we take that number and we multiply it by 0.0625. And that gives us the the internal temperature. Now we do have to check to see if it's a negative number or not. I have tested this device, with putting the probes in a freezer and then throwing the whole device in a freezer so I could test the internal and thermocouple temperatures to make sure that they worked with negatives. And then we can trim off those numbers because we're done with them. Now there's also a fault indicator and a fault indicator bit and another reserve bit. So we get rid of all of those guys, and so now we're left with the thermocouple temperature. And so we take that number and multiply it by 0.25, and then again we have to check for that negative sign bit, and that gives us our temperature in degrees Celsius. And so now we're able to go in here whenever we do an internal temperature or request internal temperature or thermocouple temperature, we go and get that data. And then if you want it in Fahrenheit, then we just do a simple calculation. Now one of the things I should point out with this module that I've written is that there was actually a pretty good article on Adafruit on thermocouple linearization. It's been a long day, and so it was an interesting article. So I thought I would include some routines for that. By default, they're commented out, but you can bring them in, and if you recompile this application, you can compile it with this routine in it as available, and then you're able to use it to calculate a corrected temperature. And this is, of course, according to the NIST calculation technique for K-type thermocouples. One other thing I should mention, this driver will also work for the GHI Electronics thermocouple module that was discontinued a while ago. And so you can use this driver with that thermocouple module, because GHI used the MAX31855 chip. There was a bit of a problem with negative temperatures on that, but like I said, if you use my driver, I've tested it and it all works with negative temperatures and stuff. So let's go in and take a look at a sample device that I built to test these. And the first thing we'll see is the Gadgeteer, the designer. You can see that these things, I've used breadboards by default in all my designers for modules. You don't have to have them. You can solder headers on as I did, and we'll see those in a bit. But what makes these so easy is that I can come down here and I can literally just drag these onto my designer and plug them in, and we're good to go. So somebody using this doesn't need to know how the thermocouple is working or any of the low-level code behind it. They can use it as just a regular Gadgeteer module. So we'll just get rid of that. We'll go in here and we'll take a look at the code that we've got. So all I'm doing here is I'm just setting up a timer, and every second it's going to go and ask for a reading. I wanted it to write to a SD card because for part of my testing I threw this thing actually into a freezer because I wanted to test that the internal temperatures for the MAX31855 handled negative temperatures correctly and such. And so I put an SD card on here. And so we'll come down here. This is just open file, write data and stuff like this. And let's come into here. So you can see with the AD8495, if you're a programmer, you've got your read proportional, read voltage, read temperature, and so you can just make these function calls. The low-level code is handled; it's in the module driver, so you don't have to worry about any of that stuff. And so you can get your temperature Celsius. Same with the Maxim chip of the 31855, you can get the same thing, internal Celsius, internal Fahrenheit. As I mentioned, both of these I included a single point calibration offset that you can put in there. Get your temperature Celsius. A sec here, we want to. And so it's really easy to use these modules, well, these breakout boards as modules now in Gadgeteer. And then again, so we're just getting the temperatures and displaying them on a little character display, and then we're able to get the faults to see if there's any faults in with the that the 31855 reported back. So we'll run this, it'll compile it up and it'll deploy it to our board. And so again, you know, when you're looking at this code, all the pin stuff and such, a user doesn't need to know this if they just install my modules on there. So let's take a look at the project board. We'll get it running. This is the Adafruit 8495 breakout board. This is the Adafruit MAX31855 breakout board, and then this is the old GHI Electronics Gadgeteer Thermocouple module. Now it also used the MAX31855, and it's wired up the same way as this guy is, so I'm able to use my driver with this module. Now, one of the things that you'll note is that I'm not using the breadboards with these breakout boards as it is in the designer. As I said, we were using these in a prototype, and we did have some space constraints. And so what I did was I soldered on some headers onto the breakout boards, and then I have these Gadgeteer extender modules that I've soldered headers onto, and then I'm able to wire it up, and then that way we were able to save you know, the required amount of space to get this to work. Now I'm using some cheap Chinese K-type thermocouple probes. You'll note that we just needed a little bit of length. Like I said, we were monitoring some biomass reactions, so we needed something where the probes could go in and measure the temperature at different depths. And so that's what this is. So now, if I start this up, we should see that it's starting to get some measurements. So this top measurement here is for the 8495. So it's saying about 22 degrees. This chap here, he's saying temperature about 25, internal temperature 24. And that's the one thing about the Max 31855 is that there's the temperature at the thermocouple probe, but there's also an internal temperature that's on the chip. And then this fellow here, he's saying about 24 degrees. Now, like I said, I built this test board up so that I could put the probes into a freezer and make sure that the negative temperatures worked on the probes, and then I threw the whole board into the freezer to make sure that these internal temperatures also would come up correctly with negative numbers. Now, one thing I should point out is wiring up these probes, sometimes I'm not particularly sure that any of the vendors pay any attention to color codes or polarity or anything like that. So sometimes when I hook these things up, you know, I'll wire them up. Then sort of my electric Kool-Aid acid test is I'll grab one of the probes because my body temperature hopefully has a higher temperature than the ambient temperature, and so I should see the temperature going up like I am here. It's up to 30.31 degrees Celsius. Now, if I had this wired up backwards, and I grabbed that probe, it would start getting colder, and then I would know that I would need to reverse these connections on the breakout board that I've got it wired up wrong. And so that's my just kind of a quick test that I always run to make sure that that we're good for the connections are proper. Now, hopefully these drivers will help some people that are using Gadgeteer. They'll be able to just take the installer, run it, and it'll add these modules to their toolbar, and they'll be able to use them as they would any other Gadgeteer module. I'll post the source code on GitHub, so if you're using .NET Microframework or .NET, that you'll be able to use the source code to be able to add couple temperature probes to your projects, and as such, I hope that this helps people understand how these drivers were built and what's kind of different about them, and how to use them. And I've got some other breakout boards that I'll post some videos on too, from SparkFun and some more from Adafruit and such, and I'll get those up as I have time to build these videos and stuff for them. So until next time, happy gadgeteering!